Hey guys, welcome back to the calculator section for the probability and counting test. Okay, we're going to be going through, just like last time, talking about each question, how I do it, what goes into it, and any common mistakes, if I can think of any. Alright, so question 5. It is believed 2 engine parts, R and S, make an engine more likely to break when running at high speeds. Of 32 engines investigated, 8 have part A, 15 have part S, and 12 have neither. So the number in R is 8, number in S is 15, and the number that is not S or R, let me just make sure I get or union, neither of those two is 12, and the total should be 32. Part A says produce a Venn diagram to illustrate this information. So Venn diagram, probably good to do the universal set here. And then we're going to have R and S. We know that there's 8 there, 15 there. I do these little bubbles in the corners to indicate how much there is in the entirety of the circle. Whether that's useful or even correct, I'm not 100% sure, but that's what I do to keep track of it. And I also know that there is 12 that is not in either of them. Well, in terms of the Venn diagram, I need to know how much is in R, S, R and S, and S in each one of those 3 spots. Okay, it's going to help me a little bit later on. So what I'm going to do is figure out, well, if there's 12 outside here, then the number in both of them, S union R, has to be 20. Okay, from the 32 take 12, there's 32 and 12 of them has neither of them, so 20 has to have one or the other. So if 20 is this whole thing, okay, let's do a little diagram. 20 is that whole thing. Okay, so how much is in just the middle here? And you might be thinking of my addition rule, probability of R and S and intersection. Okay, it's probability of R. We change this to n's because I'm actually thinking about the number of terms in each of these rather than the probability. Okay, number of terms, number of outcomes in each one, that'll do. Okay, number in R plus the number in S, elements, that's the one, number of elements. Number of elements in S, take the number of elements in both of them. Okay, what's the other word for this? I'll come back to it. In R. So you guys might remember the addition rule for non-mutually exclusive events. Alright, here it is. Here. Right, that one there. Probability of A or B is equal to the probability of A union B, because that's union is or. It's equal to probability of A, probability of B, takes probability of A and B. We've used this, but rearranged the probability of A and B and swapped it with the probability of A or B. Okay, and we're using the number of elements as opposed to the probability, but it should still be the same. Alright, so this is R, which is 8 plus 15, take 20 is in both of them. Okay, or in. Yeah, both of them. So we've got 23 take 20, which is 3. So 3 goes in the middle here, 5 goes here, and 12 goes here. In total, we should have 32. 24 and 8 makes 32. Cool. Pretty happy with my Venn diagram here. I'm going to move on to part B. Given an engine has part R, what is probability it also has? It also has part S. So probability of S given R. Well, now we're thinking about every car part that has R, or engine part. There's 8 of them. Out of those 8, 3 of them are also S. 3 out of 8 is my answer here. Okay. That bottom, the given part always becomes my new total. Are the events R and S independent? Okay, well, with independence, now I've written this up prior to this video to make sure that we could talk about it. Independent means that, and just as a little side note, if we have dependent events, we're talking about conditional probability. For independence, it means it is not affected by previous events. Okay, this might mean each flip of a coin is independent. So the previous flip of a coin, heads or result of a coin, doesn't change the result of the next one. It's always going to be a 50-50. Or we could think about the result of a coin and a roll of a dice. These are two separate things. The flip of a coin doesn't suddenly make a 6 more likely, as an example. Okay? They're independent of each other. They don't affect one another. And multiplication rule is a little side note because it directly relates to independence. We have probability of A intersection B, A and B is equal to the probability of A times by the probability of B given A. Okay, that's my conditional probability. This is the one that you'll find on the formula sheet. There it is. But if you have independence, and only for independent events, probability of B given A is still the probability of B. So this is the part that we're going to use for the question that we're doing, part C. Okay, but to finalize what I'm talking about here, probability of A and B for independent events is the probability of A times by the probability of B. Okay, we'll come back to that and we'll look at mutually exclusive events a little bit later as well. Are the events R and S independent? Well, in this case, okay, we can look at this in 2 different ways. Let me just double check, make sure I'm not going in the wrong direction. Alright, so let's try this way. Probability of R given S should be equal to the probability of just R if they are independent. So this is the question we're asking ourselves. We can do this in a different way as well, but we'll think about just this one for now. Probability of R given S is equal to the probability of R if they are independent. So we should be able to figure out both of these. Probability of R given S. Alright, well, given S means it's out of 15 here. How many of them are? Well, that's 3. Probability of R is 8 out of 32. Can these match each other, or do they match each other? And I'm pretty sure they don't. So they are not equal, which means they are not independent. That's all we need for this question. The other way you could think about it is using the full thing. Probability of R and S should be equal to the probability of R times by the probability of S. Okay. If they are independent, then this should be true. Okay. Probability of R and S is 3 out of 32 because there's 3 that is both R and S out of 32 in total for this engine part. Okay. Probability of R is 8 out of 32. Probability of S is 15 out of 32. Sorry, 1 and 4 would work there. Okay. 3 out of 32 is not equal to 15 or 128. Okay. So, they are definitely not independent. We've done it 2 different ways. We've used our multiplication rule. We've checked if that's true. Okay. Or we've used my conditional probability. If it is reliant on the other one, or if it changes with the other one, then it is dependent. If it doesn't change, then it is independent. Let's move on, and we'll talk about question 6. Let A and B be events such that probability of A intersection B, so A and B is a quarter, probability of not A is 1/3. Okay, the line above the A means not a complement. You might also see the dash instead. Okay. Probability of B is half. What is the probability of A and B? Well, this sounds a lot like the parts in my addition rule. Okay, let's take a look at the addition rule. Here, probability of, we've got A union B, A intersection B, probability of A, probability of B. It's using all 4 of those bits, which are very similar to the parts that I've got on this question. So let's try this. What is probability of A union B? Well, it should be equal to probability of A plus the probability of B. Take the probability of A intersection B. Alright, well, we know, just a little side note, what probability of not A is equal to. So the probability of A has to be the rest. That's how complementary events work. Okay, or 1 take 1/3 if you wanted to. So we know what probability of A is. This is 2/3. Okay, plus the probability of B, which we know is a half. Take the probability of A and B, which is a quarter. Fractions, we need common denominators to be able to work it out. So 12, let's do the whole thing over 12. Times by 4, 8, plus times by 6, 6, take 3, and we get 11 on 12. It's not the only way you can do it. Alright. Some people might like the two-way table idea. Alright, you can set yourself up like this. Then you can say the probability of A is, or probability of not A is 1/3. Probability should all come together as 1. Probability of B is a half, so not B is also a half, and probability of A and B is a quarter, and then you should be able to work out what the rest is from your adding and subtracting two-way table stuff, and then you should be able to figure out what each of those parts are that you need, or probability of A and B, probability of B not A, and probability of not B and A. Those 3 added together would get you the probability of A union B. Okay, it also goes to our Venn diagrams. which we can do. So as I said, lots of ways to be thinking about it. We know that there's a quarter in the middle. Probability of B and not A is also a quarter. You can figure out what that part is eventually. 2/3 take a quarter. Anyways, lots of ways to think about that, but I believe the addition rule, if you recognize each of those parts as being part of it, then you can work that out pretty quickly and algebraically instead. Alright, it is only 3 marks, don't spend too much time on it. Question 7. Consider the digits 0 to 9 inclusive and the letters of the alphabet. 8 characters are chosen at random. Determine when order is not important. Okay, order is not important. We are thinking about our combinations choose function. Okay, the opposite being permutations, where we haven't done a whole lot of this in my class. This is when order does matter, so we're not doing that one. Part A, the number of ways of choosing any combination of letters and numbers. Well, how many letters and numbers are there in total? There's 26 letters of the alphabet. You can count it out if you want to. And 0 to 9 is 10, so there's 36 characters in total. And we are choosing 8 of them. 36, choose 8. Now, this is the calc section, and we actually do want to work that out. So where do I find my choose function? Either on my TI or in my scientific calculator. Scientific calculator might be easier, but anyways. Menu, probability, combinations. And well, there it is. 36, 8. Okay. That is a lot of combinations. That's when order is not important. Crazy. Part B, the number of ways of choosing any 6 digits and any 2 letters. Okay, so we're going to choose 6 out of my digits. Sorry, let me switch back to here. 6 of my 10 digits and 2 of my 26 letters. Alright, so I'm going to do menu 5, 3, 10, 6, sorry, times menu 5, 3, 26, 2. What's that number? 6, 8, 2, 5, 0. So there's 68,250 ways of choosing 6 digits and 2 letters. Part C is the probability of choosing 6 digits and 2 letters. Okay, probability means I've got to do out of the total number of combinations. Okay, total number of combinations actually comes from part A, the number of ways of choosing any combination of letters and numbers. So I know that there's 3, 0, 2, 6, 0, 3, 4, 0. And 6, 8, 2, 5, 0, number of ways of choosing 6 digits and 2 letters. So 68,250 out of 30 million, so on, gives me my probability. Or we could write this as 10 choose 6 times 26 choose 2 over 36 choose 8. And I've already worked out what each of these are in my calculator, so I'm going to use each of these. This divided by this, 2275 on 0.008678. And if we wanted a decimal, cool. And then part D, the number of ways of choosing 4 odd numbers and 4 consonants. Consonants being not vowels. The number of ways of choosing 4 odd numbers. How many odd numbers are there? Well, there's 1, 3, 5, 7, 9 in my odd numbers. So 5, and I'm choosing 4 of them, times by, there's how many vowels? There's 5 vowels, A, E, I, O, U. Okay, so there would be 21 consonants, and we're choosing, 4 of them, not 5. 5 choose 4, times 21 choose 4. And 3, 5 choose 4, times by 3, 21 choose 4. Whoops. 29,925. Cool. Question 8. The bag contains 5 red buttons, 2 blue buttons, and 6 green buttons. 2 buttons are chosen from the bag, one after the other, and the first button is not replaced before the second one is selected. Part A. Show the sample space of this experiment by drawing a tree diagram. So tree diagrams directly link, or usually link, to my conditional probability. We have 3 options: red, blue, or green. Okay, there's 5 out of 5 plus 2 plus 6, there is 13 buttons. So we can get 5 out of 13 is probability of choosing a red one, 2 out of 13 is the probability of choosing blue, and 6 out of 13 is the probability of choosing green. Then, depending on which button we've chosen on the first draw, then this changes what the result is for the second one. Okay, these are directly dependent on the result of the first one. Conditional probability or dependent events. So if I have chosen a red, let me just fill in the rest of this tree diagram. Red, blue, green, red, blue, green, red, blue, green. Cool. If I've chosen a red, then there is only 4 red tokens, buttons left, and there is only 12 in total. Okay. Blue, still 2, but it's still out of 12, and 6 out of 12 here. 5 out of 12 here, and that's a little bit messy. I might have to fix that one up. 5 out of 12 here. If I've chosen a blue one, there is 1 out of 12 left. Green, there is 6 out of 12. 5 out of 12. Red, if I've chosen a green, 2 out of 12 I've chosen blue, and 5 out of 12 I've chosen, I'm choosing a green if I've already chosen that green. Not my best tree diagram. I guess this would be a demonstration of making sure you give yourself enough room. Okay, common mistake for me. There is my tree diagram. I've labeled each with my with each of my probabilities. Okay, make sure I haven't forgotten to say anything. With your tree diagrams, the important part is that each branch or set of branches is mutually exclusive, I believe would be the best way to say this. Okay, I do have a habit of mixing up independent and mutually exclusive. Okay, be better than me, practice lots. Each set of branches is mutually exclusive so that if I have probability of A or B, or would be the union. Okay. Essentially all I'm saying here is that I can add sets of my branches if I'm doing my tree diagrams, which is important for these questions because part B, what is the probability that both buttons are the same color? Now, there are several ways that I can get the same color button. I can get red, red, or blue, blue, or green, green. Now, with tree diagrams, it's important that they're mutually exclusive. Otherwise, there's no crossover between the red, red and the blue, blue, so I don't have to do the addition rule where I take the probability of both of them happening at the same time, which we've seen earlier in, which question was it? All right, question 6 was where we saw it. Anyways, thanks Windows, appreciate it. See fewer notifications. So, probability of red, red has to be on my tree diagram here. I get a red first, which is 5 out of 13. Then I get red second, which is 4 out of 12. Probability of red, and then red is 5 out of 13 times 4 out of 12 plus, okay, blue, blue would be 12 out of 13 and 1 out of 12. So that's green, green, which is 6 out of 13 times by 5 out of 12. Okay, these are each situations where I can get the same color, both red, both blue, both green. So adding those all up together, not there, the actual calculator, I've got 5 out of 13 times by 4 out of 12 plus 12 out of 13 times 1 out of 12 plus 6 out of 13 times 5 out of 12. Yep. Doesn't look quite right. Maybe I'll double check using my fraction button. That should still work. 5 out of 13 times by 4 out of 12 plus 12 out of 13 times 1 out of 12. Oops. That's not right. It's supposed to be 2 out of 13. That's what I've made the mistake on. Times by 6 out of 13 plus times. These are the things that we make mistakes on the test, and then we can't go back, or we forget to go back, or we don't realize because we're under the pump of time. But that's a bit better. Cool. 1/3, 5, 4, 2, 1, 6, 5, 13, 12, 13, 12, 13, 12. Times add, times add, times add. Yeah, looks good to me now. We can move on to part B. What is probability that the second button chosen is blue? So we can get red blue or blue blue or green blue. Okay, in each one of these cases, the second button that we've chosen is blue. Okay, so let's do this. Red blue is 5 out of 13, and then 2 out of 12 plus 2 out of 13 times 1 out of 12 plus 6 out of 13 times 2 out of 12. That looks good. Um, 5 out of 13 times 2 out of 12 plus 2 out of 13 times 1 out of 12 plus 6 out of 13 times 2 out of 12. 2 out of 13. 2, 2, 1, 6, 2, 13, 12, 13, 12. Alright, that's part C. And then what is the probability that the second button is red given that the first one was green? The probability of the second red given first green. Now the thing about my tree diagrams is they've actually given me a lot of these, all of these probabilities anyways. I don't have to do the conditional probability formula where I'm doing the probability of both of them occurring over the probability of the green, because probability that the first one is green is now just this set of options. Okay, that is where the first probability that the first one is green, those are my totals now. That's out of those options is all I'm looking at. That's the one. Because the first one is green, I am now restricting myself to just these options. These already add to 1, so my total is out of 1 here, and I am looking for a red, 5 out of 12. So that's my answer here. What's the probability that the second button is red, given that the first one is green? First one's green, what is the probability that the second one's red? 5 out of 12. Cool. I still got one more. Cool. Let's go through it. 2 subsets, question 9. 2 subsets M and S belong to a universal set of 200 students. Okay, students belonging to subset M have attended a mathematics revision seminar, and students belonging to subset S have attended a science revision seminar. It is known that the number that was in M is 58, and the number in S is 40, and the number in M or M union S is 81. Okay, use this information to complete all of the regions of the Venn diagram below. Well, if we know that everything in M and S is 81, then we know that everything else, the 119 out of the 200, has to be doing neither of them. Okay. Now, because of this overlap here, we can do something very similar that we did to question I think it was right at the beginning. Make sure. Yep, question 5a, we've done something exactly like this. Okay. Probability of, number of elements in M plus the number of elements in S, take the number of elements in S union M, or vice versa, gives me the number of elements in S and M. Okay, so I'm doing 58 plus 40, take 81, which gives me 17. So 41 has to be on this side, and 23 has to be on this side. Okay, this is going to be useful to have in the questions that I'm about to do in part B. If a student is selected at random from the group, determine probability is not M or S. Okay, not M or S. We're looking at the total group of 200 students, and we want to know whether they are not in the math seminar, so the 23 plus 119 plus the people that are in S is the 17. So pretty much all we're trying to find is just those added together. That's 23 plus 119 plus 17, 159 out of 200. Did the science seminar or didn't do the math seminar? Didn't do the math seminar, or they did do the science. So everyone but the people that did the math seminar. Yeah. Cool, 159 out of 200, and then part 2 here, we've got the probability of not M, given that it is not S. Well, how many people aren't in S? Let's go here. Aren't in S is anything outside of the S circle, so 41 and 119, so 160 in total here. And then how many people didn't do the math seminar is anything outside of, scratch that. We've done everyone that was not in the science seminar, and we need to count the number of people that were not in the math seminar, so just the 119 here, okay, because we are looking for the probability is not M and it is not S. Out of probability, it is not S if you're going with the conditional probability formula. Probability is not S. Oh, not quite probability here, but that's how the formula works. The fractions would cancel anyway. 160, 119 out of 160. That's it. Okay, if you wanted to, you could do it as a separate fraction. There's 160 out of 200 that didn't do the science seminar, and that there was 119 out of 200 that didn't do either. That out of 200 is going to cancel and give you the same fraction that we've got here. We can just think about the number of elements in this case, but this would be more accurate or more following this formula here. Anyways, are the events M and S mutually exclusive? So this goes to the notes that I have written earlier. Mutually exclusive, what does that mean? It means that they cannot occur at the same time. Here would be a diagram of mutual exclusivity. Okay, A and B cannot happen. There's no crossover between them. Okay, so for example, this would be like kings and aces. You can't have a king that is also an ace, so it's mutually exclusive. Kings and hearts are not mutually exclusive because you can have a king of hearts. They can happen at the same time. And if we were looking at our addition rule, which we've seen a couple times in this video, probability of A or B is equal to the probability of A plus probability of B. Take the probability of A and B, but for mutually exclusive events, they can't occur at the same time. So this probability of A and B, there's nothing here. So that goes to 0, which means we have probability of A or B is equal to the probability of A and B. And so with our mutual exclusivity here, okay, all we need to know is the probability of M intersection S equal to 0. Okay. If it is, if they don't happen at the same time, so they're not at the maths, so they didn't go to both the math seminar and the science seminar, okay, then we can say that they are mutually exclusive, but 17 people did. So, no, probability of math and science seminar is not equal to 0. That's all the evidence we need to solve that one. Cool, that's the end of this video. I hope it helps. Let me know if you've got any more questions. Probability can be a pretty overwhelming topic and they can get quite hard. So, good luck. Let me know how you go.